Testing, can the chat hear me? Okay, everybody, so as always, remember to do the seating survey. Upcoming deadlines, homework 5 is finally due tomorrow after a long break for that. There are going to be new videos, content videos, and a small group activity coming out very, very soon. And along with a what to expect week 7. Please note that because of the delay we had this week, our week number and homework numbers are no longer matching up. So just be aware of that. The next batch of content video quizzes will be due next Wednesday, and the small group activity that is going to be on kinetics and is specifically going to be looking at radioactive decay with respect to measuring the age of the Earth is going to be due not next Tuesday, but the following Tuesday. Does anybody have any logistics stuff to talk about before we get into the single muddiest point that I got? No? Okay. So we did do a lot of kinetics muddiest points yesterday. As always, the topic index is on Blackboard for the video of that. So, but I'm of course happy to answer other questions that we have here today. Apparently, some of the homework questions may be assuming that you know something about the molar extinction coefficient or spectroscopy or Beer's law. And I had not anticipated that as I was putting the homeworks together. So I'm going to give you a brief intro to what's going on with that. I think some of you have seen this in lab already, but I do want to give a slight introduction to it. So the general idea is that if you shine light, so we have our light bulb here, shine light through a sample, usually a solution of some sort, and you measure the absorbance, which is a measure of how much of the light gets blocked by the sample or gets absorbed by the sample. Then that quantity, the absorbance, is related to the concentration of the sample. So the way this works is that you can measure what's known as the percent transmittance. So if 50% of the light comes through, then your percent transmittance is 0.5 or 50%. But you measure the transmittance. I guess we don't do it in that mode as a percentage. We can convert that into an absorbance, which is the negative log base 10 of the transmittance. Okay, and so we call this A, the absorbance. And so think of this as like having food coloring that you have put into some water. If you put in 2 drops of it, it will block twice as much light. So this is a way to measure concentration. So the absorbance, according to Beer's law, is epsilon, which is the molar extinction coefficient, which we're going to get to in a second, times the concentration in units of molarity times the path length of the sample cell. So very, very often we will use a standard sized cell which has a path length of 1 centimeter. So, if you have the light passing through twice as long a path through the sample, then you would also expect you to have half as much light getting through. So if we know L, if we know epsilon, and if we can measure A in a spectrometer, then we can calculate the concentration. And that's the general idea of this approach. So what is this epsilon thing? Well, it depends on what your solute is, and it depends on which wavelength of light you're looking at. So food coloring, as you might imagine, will absorb, yellow food coloring, for example, would absorb yellow light differently from, say, blue light. Okay, so this is a quantity you would have to either be given, or what you could do is measure, have a known concentration of a sample that you make, plug it into this, measure the absorbance, and then you can calculate the extinction coefficient from it. So if you, that's the general idea. So why is this particularly useful for us at this stage in chemistry? Well, because so much of what we're doing with kinetics involves measuring the concentration of something as a function of time, and either watching it disappear, or if it's a product, watching it appear. Right? So what you can do is find a wavelength of light where the species you're interested in, either reactant or product, absorbs, but nothing else does. Then you put your reaction mixture into your spectrometer and set it up so that it takes a measurement of absorbance every 10 seconds or every 5 seconds, or if you have a really fast system, every microsecond, something like that. And so since the equation here, as over the course of the reaction, epsilon doesn't change and path length doesn't change, then you just have to do a simple scaling factor to convert your absorbance as a function of time into concentration as a function of time. That's the general idea of why this is extremely useful, extremely powerful at this point in kinetics. General idea. So question here, can you do an example of this? I don't know any extinction coefficients off the top of my head, but the general idea would very simply be if you are given the extinction coefficient and you measure absorbance as a function of time, so given this, you're measuring absorbance as a function of time. Let's say we're looking at a reactant that's going away. Let's suppose that this has a value of 3,000 per molar per centimeter, something like that. And we make an absorbance measurement of 1 at time equals 0. And at some time here, we have an absorbance of 0.5. At some time here, we have an absorbance of 0.25. At some time here, we have an absorbance of 0.125. So what I'm doing here is plotting out a first order kinetic process. Then each of these absorbances, we go to our formula, and what we do is we then take the absorbance divided by our extinction coefficient, divided by our path length, and let's assume we're dealing with a 1 centimeter path length. And so the absorbance here becomes whatever 1 over 3,000 is. And so that would, I'm sorry, the concentration becomes that. So 1 over 3,000, and if we look at the units, it's going to be molar, because if this is per molar per centimeter, the per centimeters cancel. The molar, molar and per molar would cancel, and the absorbance here is a unitless quantity. So, this value here would be 1 over 3,000. This value here would be 0.5 over 3,000 molar, and so on. So that's the general idea of how you would do this. Any questions on this concept that we're dealing with? Okay. So, I am happy to open up questions on any of the subject matter. It is very possible, though, that given that you guys now have had 2 weeks where you've been looking at this homework, you may have either gotten it done or be on top of that, in which case I'm happy to talk about anything you guys might want to, including perhaps doing some brainstorming about what some types of exam questions that might be over this material might look like. So what do you guys want to do? Yes.
Would you be asking a question about lambda max and then the concentration at lambda max? Or...
Right. Okay. So the question for folks in the chat is would I ask questions about lambda max or the concentration based on a lambda max or something like this? So the idea of a lambda max, let me explain what it's about, and then I'll answer the question about what I might ask about it. The idea is that if you measure the absorbance as a function of wavelength of light, then you're going to end up with some kind of spectrum. This is called a spectrum. And generally, when you are wanting to measure a concentration of something, you want to have the largest absorbances possible so that you have the most precision in your measurement. So you would be going to, so you would typically pick the wavelength for your measurements to be what we call the lambda max, or the maximum value, the wavelength at which there is maximum absorbance. It's not always the case that you want to do that. So for example, if we had a case where something else in this same sample absorbed like this, then two things would be absorbing there. Over here, there are not two things, so you might pick something other than the lambda max in some situations, but that's going to depend upon looking at multiple spectra to figure that out. Now, am I likely to ask you questions about this kind of thing? Well, given that I haven't given you a content video on it, I am probably not going to be asking questions about this specifically. So I'm primarily introducing these ideas for the, so that you have access to this information for the Newton homeworks in the cases where it's asking for information on it. Okay, there is a request from the chat. Can you do an example on empirical rate laws and the method of initial rates? I had a hard time understanding the video and the Newton assignment on it. I'm happy to do that. So let's see how we can do this. So the idea is if we imagine some kind of measured concentration as a function of time, and we measure the initial rate, so the initial slope, we'll call that R0. There is a way to use that information, the initial rates, to figure out what your rate law is. So this is a complementary technique to the method of flooding, which I've talked about several times here in class. Both of those methods can get you the rate law relatively straightforward, in a relatively straightforward fashion. The advantage of the method of flooding is that you don't have to be making this initial rate measurement very precisely. You have to make sure that you have enough data right at the beginning, very precisely measured, in order to get that initial rate pretty well. But on the other hand, there may be some systems where you don't have enough of a range in the concentrations you can use in order to really flood the system with all of the reactants except one. Maybe solubilities are limiting you or something like that, in which case the method of flooding wouldn't work very well and the method of initial rates would. So even though these are two different ways to get at the same information, they can sometimes be useful in different contexts. So let us look at how we can use R0 information to find find a rate law. So let us suppose we know that our rate is going to be some rate coefficient, concentration of A to some power, concentration of B to some power, concentration of C to some power. Okay. Now, if we are looking at the initial rate, then we'll label that R0. We have the rate coefficient is the same always, it's a constant, but we also know the initial concentrations just by preparation of the sample. Okay, so what we can do now is makes measurements of this initial rate at some different concentrations of these reactants or products or whatever they are, and use this formula in a clever way by ratioing the different reactions to give us the rate law. So let's look at how we might do that. So let's set up a table. A0, B0, C0, and the measured R0 that we would get. So we'll do all of these concentrations in molarity, and we'll do the rate we will say is in is in something like per second, per molar per second, or molar per second, right? That's what we want. So let's suppose that we have 0.1 molar. Let's just start everything at 0.1 molar. And then we make the measurement and we find out that the result is, say, 10 molar per second. Let's do another measurement where we double one of them. And we get 20. Okay. Let's double a different one. This time we get 40. Let's double the third one. And let's say we get 5. Okay, let's see how we can use this information to figure out the rate law. So what we're going to do is we're going to take this expression here for and let me label these. A, B, I'm using A and B for the compounds. We'll use Roman numerals. Okay. All right. So what we're going to do is ratio R0 1 to R0 reaction 2. So what we can do now is write this across for both of them. Excuse me, let me do this backwards. Let's do 2 on top, 1 on bottom. That's easier because when we do 0.2 over 0.1, we're not dealing with a fraction. So what we have here is our rate coefficient, our initial concentration for reaction 2, initial concentration for reaction 2, still reaction 2, initial concentration for reaction 2 over rate coefficient, initial concentration for reaction 1, initial concentration for reaction 1, and initial concentration for reaction 1. Now, looking specifically at the data we have, our initial concentration of B is the same in these two cases. So these cancel. Our initial concentration of C are the same in these two cases, so the C's cancel, and the K is the same in both cases, so the K's cancel. Now we can plug in the numbers. 0.2 over 0.1, and 20 over 10 raised to the A power. Everybody see this? What was that? Oh, okay. Thank you. Yep. All right. So does everybody see this? All right. So if we look at this, 0.2 over 0.1 is 2. 20 over 10 is 2. And so what is the correct value for A? 1, correct. All right, so we now know, we can go back to our rate law, and we can say we now know A, it's a 1, so we can just get rid of it there because raising anything to the 1 power is just itself. Now, let's look at comparing experiment 1 with experiment 3, where we're changing B. Okay. So we do the same kind of thing that we did here. We're going to write out R03 over R01. But this time I'm going to save us some steps by going ahead and mentally canceling the things that are the same. So the K's are always going to be the same. And looking at 1 and 3, the A's are the same and the C's are the same, so the only thing that changes is the B. So we need to put concentration of B, not 3 to the B power, over B not 1 to the B power. We can now put in our numbers. We have 40 over 10, and we have 0.2 over 0.1. I did this wrong, didn't I? These should be swapped. Let's back up to this one. R naught 2 is 20. R naught 1 is 10. A naught 2 is 0.2. A naught 1 is 0.1. So the result is the same, but I had swapped which I was looking at, the R's versus the concentrations. Okay, everybody, does that correction make sense to everybody? Okay, good. All right, so we're doing the same thing here for the comparison of 3 to 1. This is raised to the B power. And so on this side we have 4, and on this side we have 2 to the B. So what is the value of B? 2, correct. All right, so B equals 2. Now let's finally look at C. So for this one, we are going to be comparing experiment 4 with experiment 1. So we are looking at R naught 4 over R naught 1. Well, let's see. The K's cancel, the A's cancel, the B's cancel, so C is the only one that is changing. So this is going to be concentration of C in experiment 4. I have those backwards, not 4. C naught 1. Each of these raised to the C power. Let's plug in our numbers. We have 5 over 10 is 0.2 over 0.1 to the C. So this one becomes 1/2, and this becomes 2 to the C. So what is C to go from 2 to 1/2? Everybody know? Yeah? -1, that's right. C to the -1 is, I'm sorry, 2 to the -1 is 1/2. So we now have our rate law of K, concentration of A, concentration of B squared times concentration of C to the -1. So that is how we use the method of initial rates. Now, it is critical when you are doing the method of initial rates that you set up the experiments so that only one concentration is changing between two experiments. Otherwise, you'll end up with two exponents that you don't know that you're having to deal with at the same time, and the math gets hairy at that point. Now, I did in this case pick easy examples, easy multiples for the differences in concentration. There are, I believe, some Newton examples where easy concentrations were not chosen. So let's look at how that might work. So let us suppose that when we look at our rates, we get something like now what am I going to do? I don't know what I'm going to do. Let's do 1.6 over 1.2, and we perhaps chose concentrations that were 0.3 and 0.18. And so this is going to be to some power. Okay, so in this case, you're not going to be able to look at it and just say, oh, I know what power it's going to be. So I don't know if I've picked anything here where the A is going to end up being a reasonable A, but let's do it and figure out. So if I do this ratio over here, we get 1.33. On this side, we have 0.3 divided by 0.18 is going to be a 1.67 to the A. And so the way that we then are able to get the A out of an exponent so we can solve for A is that we take logarithms of both sides. It doesn't matter whether you use natural logarithms, log base 10, log base anything, as long as you're consistent and do the same one on both sides. So if we take the log of 1.33 equals the log of 1.67 to the A, one of the properties of logarithms is that when you have a power here, you can pull it out to become a coefficient of the logarithm. Okay. So now what we can do is plug this into our calculator, plug this into our calculator, divide, and solve for A. So what we will do here, if I can get my calculator to do it, is to say 1.33, where's my log button? We'll do log base 10, divided by, open parentheses, the 1.67 log base 10, close parentheses, equals, and we get an A of 0.556. So in this particular case, I did not pick randomly numbers that happen to give us a likely exponent. In a real problem, it would be closer to some value. You might be able to look at this and say, yeah, that's probably a half order reaction, which we've said that you can have half orders sometimes. But the procedure here is the important point, is how you would go through it to figure out what the exponent is. Any questions on method of initial rates? Let's see here. How do you determine which experiments to compare to each other? Right, so what you do is if you're given the experiments already done, what you look at is to try to identify a pair where only one thing changes. And so if we have this one and we have this one, then the one thing that changes is the A, so that lets us know that that will let us determine the order with respect to A. But you wouldn't want to do a comparison of, say, experiment 2 and experiment 3, because A changes and B also changes. Okay, so that's what you look for that. Okay, anything else? In normal situations, would we really get a negative exponent? You absolutely could. Negative reaction orders are possible. The idea is that if you have a negative reaction order, then whatever the species is you're talking about, the rate of reaction is going down as as that species gets more prominent. It gets a higher concentration. So there are two kinds of situations I can think of where that is commonly the case. The first is if you have a dynamic equilibrium. So you have a reaction going forward, and that's the reaction that you're measuring, but there is a reverse reaction that takes the products and regenerates the reactants. In that kind of situation, the more products you get, the faster the reverse reaction goes, which means that if you're looking at the forward reaction, it seems to slow down overall when you have that, have more of the products showing up. The second type of example I can think of is when you have an inhibitor molecule. So, for example, we have a lot of biochemical processes that go on in our bodies that are mediated by enzymes as a catalyst. A catalyst is a species that is neither a reactant nor a product, but it participates in the reaction. So something will attach to it, the reaction happens, and then it detaches, so the catalyst is left unchanged net in what's going on. Now imagine that you have one of these catalysts, but you add in something to the reaction mixture that's going to attach to the catalyst as well and will block your reactants from being able to attach to it. That would be known as an inhibitor, and the more of that you have, the slower the reaction will go. And so the reaction order with respect to an inhibitor would be negative. That general concept makes some sense? Yeah, okay. All right, what else can we talk about? Yes? Oh, determining the value of K as well. Okay, so the easiest way to do that, if you're doing sort of a method of initial rates here, is to realize once you know A, B, and C, then you have everything for this equation other than K. So you can just plug in 0.1, 0.1, 0.1, 10, and solve for K. It's the same idea as well if you're doing method of flooding. In method of flooding, the first series of experiments that you do are to determine the reaction orders. And then once you have the reaction orders, you take any one of the experiments and just plug them into the rate law, and you get the rate coefficient at that point. What else? I'm going to brainstorm a little bit about what kind of exam questions I might be thinking about for this kind of material. Would that be useful? Okay. So what I'm contemplating is giving you guys a spreadsheet, an Excel spreadsheet, where at the top of it you can design your own experiment. You would design what are the concentrations you want to put in. And then it will calculate for you using, it'll probably be a protected spreadsheet, so you won't see the formulas and such. It'll calculate for you simulated experimental data that you then could take, copy and paste it into your own spreadsheet, and then do things like take the natural logarithm as it goes down and plot it versus time. Do you get a straight line? If you do, then you've determined its first order. You then can, from the slope, determine the rate constant. Then if there are multiple components, you could use either the method of flooding or the method of initial rates to determine what the full rate law would be at that point. So if I were going to do something like that, as I am kind of leaning towards doing right now, I would give you an example version of this kind of spreadsheet beforehand, and I would also make a video where I would talk you through the kinds of Excel manipulations that you would need to do the kinds of data analysis you would want. How do you take an entire set of data and take the logarithm of all the entries, for example? How do you plot it? How do you fit a trend line to it so that you can determine the rate coefficient? So the idea there would be, I know that some people are more more adept at using something like Excel than others, and having experience with Excel is not a prerequisite to this class. So I don't expect you to come in being able to really do that, but it's not incredibly difficult to do, and so I would give you a tutorial on how to do the manipulations that would be necessary. So the thing I like about that kind of question is that it's not very, even in upper division chemistry classes, it's not very often that you get to think about experimental design, about, okay, if I had to choose which concentration to use, which ones would I choose and why would I choose those? And that's a, so that's, because practicing scientists have to make those kinds of decisions all the time, I think that getting people to start thinking along those routes, how many data points should I take? How many different concentration combinations should I do? That gets you thinking about the realities of scientific data. So that's kind of where I'm leaning towards for this kind of material. What else can we talk about? Are people feeling relatively comfortable with the first week's worth of kinetics stuff, generally? Okay. Can I do an example with half-life? Okay, sure. So what I would do for half-life, I'm actually going to look up some data because I have an interesting idea for this. So here we go. Okay, so plutonium 241 has a half-life of 14.4 years. And plutonium is extremely radioactive, and so if there is a sample of plutonium 241, then it's dangerous to have around. So let's think about how long this sample would need to sit around in order for the amount of plutonium 241 to be, let's say, 1% of the original amount that we had. So, at that point, we might say maybe that passes some threshold that the sample would then be safe to deal with again, or something like that. So that's the kind of idea. So we have our relationship between half-life and rate coefficient, which for a radioactive decay, we know radioactive decay happens by a first-order process. So we have that T1/2 equals the natural log of 2 over the rate coefficient. So we can find the rate coefficient just by solving this the other way around, over 14.4 years. And so, calculator, so let's do 2 natural log divided by 14.4. And we have a K of 0.0481. And what are our units here? Well, natural log of 2 doesn't have any units. We have years here. So what are the units here? What's that? Well, it's in the denominator. Years to the -1, right. So you can write it like this, or you can say per year. All right. So now that we have the rate constant, we can use our first order expression. Here. And we're trying to get the concentration here to be 1% of the concentration here, right? So what that means is if we divide through by A0, okay, we want this ratio to be 0.01. Okay, so how do we get rid of the E that's over here? Mathematically, what do we do? We're trying to solve for T. Yes? Natural log. Yep. So natural log of 0.01 equals minus K, which in this case is 0.0481. Oops, I'm off screen bottom. Years minus 1 times T. Natural log of 0.01, natural log, we get negative 4.605 equals negative 0.0481 years to the -1 times T. So negatives are going to cancel. We'll divide through here. So we have 4.605 divided by 0.0481, and we get T equals 95.7. And what are our units? We brought years to the -1 over to the other side by dividing through. So that brings it to the numerator again. So years. So this says that for a radioactive isotope with a half-life of 14.4 years, our sample will be down to 1% of its original amount in just under 100 years. So that's the kind of problem I would think of to do with half-lives. I know that in the content video when I was introducing half-lives, I took you through the formulas for second-order half-lives and zeroth-order half-lives. Because those half-lives still have the initial concentration in their formulas, unlike the first-order case, they are not very useful. And so I personally would not ask you a question using those, because in practical chemical kinetics, nobody talks about half-lives for anything other than first order. The main point of going through that was just to illustrate that, that they don't have a well-defined half-life unless it's first order. Okay. How do you do natural log on the calculator? Well, hopefully your calculator will say ln somewhere. On the iPhone, it's right here. So it's usually right close to the log base 10 button. Anything else we can talk about? If people want to call it early today, I'm happy to do that too. Up to what everybody wants. All right, well, let's thank you all for coming. I will have more content videos and the small group activity out within a couple days. And we will get back on track in terms of getting through new material. Thanks.